But ours, you like me to spy along.
All right. How's everyone doing today? Everyone stay safe yesterday? All right. Gathering thoughts. Today we're going to begin chapter 1, which is very much the intro to the course, scientific method and measurement and all that. Before we get started, first of all, any questions, needs, concerns from anybody, including anything about Brightspace? Because I think at this point everyone should be in the course, but if you're still not, I would appreciate a reminder. I submitted a request for everybody who emailed me on Monday, which I do greatly appreciate, and I've checked over all the lists. Everyone should be in by now, but if I missed something, please do still let me know. Anything at all on your minds before we begin today? All right. Now, is that? Since everyone should now hopefully have Brightspace access, let's look back at the Brightspace classroom real quick, just to point out where you can find the slideshow I'm about to put on screen if you care to follow along with it. So once again, the course you should be able to see now should say Hoffbauer, Physics of How Things Work, Spring 2024. The intro tab has the syllabus, formula sheet, and the welcome notes from Monday. As we go through the chapters, there will be tabs for each specific one, numbered as they are in the book the course is based on. Within that tab itself mentions the homework questions you should be able to do by the end of the time, by the time we finish talking about everything in a specific chapter. And the slides that I present always go right here. Now, we're going to cover about a chapter a week, usually, based on how the textbook numbers things. And the notes will be a little bit in flux, because sometimes I'll have the slides I use ready by Monday, and then by Wednesday I think of a new example I want to do or a better way to phrase something. So sometimes what's uploaded here might be a little different to what I present, just as I edit my presentation draft. So I'll try to update the copy that's saved here as the week goes on. But this is where it will always be, within the specific chapter tab on Brightspace, so you will always have access to them. And with that said, let's begin talking about our first section in this particular course. That's going to be primarily about the tools we're going to need to be able to do physics. Now, I'm a bit biased when I say this because I am a physicist, but I like to think of physics as one of the most foundational sciences, bless you, because it really is the study of everything. If you see something happening in the universe, a physicist is going to look at that and think, why, how, what can I do about that? As I said on Monday, whenever you observe the universe around you and try to notice patterns and draw conclusions, you are doing physics. And as a result of this, physics, in my opinion, kind of relates to everything that you do. It can relate to about every single field of study one could possibly study. I also tend to think of physics as a very foundational science, in that it is one of the most, in my opinion, again, I am biased, objective things you can study. And what I mean by objective is that physics tries to study the universe directly and try to draw as close to factual conclusions as we can. we do interpret the universe around us, but we're trying to interpret as much of the raw data as we can without trying to input like basically human feelings about it. And as a result, we tend to think of physics as more on the objective side of study compared to subjective fields of study like art and literature, which are all about human emotion. So I always like physics as a result of that, since it's a very objective science. It's very rooted in math, because math is, again, I'm kind of biased here, the most objective thing you can study. Math just is. A number either is something or it is not something, and there's not really any room for interpretation there. So on this chart that I usually draw, I think of math as the most objective thing you can possibly study, and physics is only one tick mark to the right of math. And that's because we need math to be able to do physics. Physics is literally interpreting the universe around us through the lens of math. Math is the most objective because it either is or it isn't. Physics, we use the math, and since there's human interpretation in doing physics, it's a little less objective than the math itself. But because it's way over here, because physics is way over here in the objective side of things you can study, that literally makes it a hard science. Not necessarily meaning difficult, but just in that the rules that we try to study with physics tend to be pretty set in stone. Gravity's going to keep doing what gravity's going to keep doing, and human interpretation really just is trying to logic out why it does that. And as you continue along the disciplinary track from here, things tend to get a little less objective and a little more subjective. And again, I'm a physicist, so I'm going to talk about physics like it's a foundational science because I like physics. I think it's very important, but you might get a different perspective from a different type of scientist. But as you go down this pathway, you just kind of apply the previous thing to the next thing as things get a little more subjective. For example, chemistry, I would say, is applied physics. You apply information about the universe specifically to chemical reactions and elemental science. Biology is applied chemistry. The chemical reactions that go on inside of a biological organism, it is applied chemistry. You know, biology is literally a bunch of chemical reactions within an organism. And then after biology, things get progressively more subjective as you enter things like psychology and sociology and economics, and eventually you get all the way to the most subjective thing, which is art. Now, why did I go through all of this? Physics is, in my opinion, about as sciencey as you can get. It's a hard science. The rules we're trying to study here, the universe we're trying to study, is pretty set in stone. And it's our job to use math and logic to try to figure out what's going on. So the math is kind of inescapable. We're going to be using the math as a tool to study the universe around us. And because physics is, again, in my opinion, the most sciencey of sciences, it's the one furthest to the right on this chart that I use in my head, we have to be very careful in how we perform the scientific method. Which, is anyone unfamiliar with the scientific method? Okay, just checking. So, to review, the scientific method is the list of steps that one has to undertake to be as scientific as possible, to do good science. And I want to refamiliarize ourselves with these particular steps because we're going to be trying to do real science as much as we can throughout the entire semester. We need to measure things, draw conclusions, and calculate things based on our measurements. So if physics is as sciencey as I like to think it is, we have to follow these rules. So let's get them down in our notes and remind ourselves what these rules are. So these will kind of be the guidelines for how we perform experimentation and logical thought processes throughout the entire semester. there is, the way that I write them, 8 steps to the scientific method. And first step, you have to observe something happening around you, and you have to question why that is. And frankly, humans are pretty good at that. Because as I said on Monday, you've been making observations about the universe your entire life. You see something happen, and you wonder, whoa, why was that? You know, why did that thing fall? Why is the floor of my dorm super cold when I wake up? Why did that thing shock me just now? Any observation followed by any question about why that happened. That's the first step of science. So as long as you do that every day, you're already a pretty good scientist. The next step is performing research. In the first step, you asked a question about why something happened, and then step 2 is researching why that happened. And humans are pretty good about that too, because most of us own net-connected supercomputers that are able to tell us the answers to most things that we already have questions to. So if you Google something, you're also already a pretty good scientist. Now, you have a question, you look it up, you get your answer, that's already science. And for a lot of questions, that's about where it ends. Humans have done a lot of research over the years. However, there are still questions that have yet to be satisfyingly answered. And so if you do the research and you do not find an answer to your question, we have to proceed to step 3. We have to form a hypothesis as to why the thing we observed happened. And hypothesis really is just a $3 word for an idea. Hypothesis is just an idea. It is your best guess at that moment as to why that thing you observed happened. It's just an idea, produced from your human brain. A good hypothesis includes initial conditions. We'll talk about that a little bit later, which is just to say that when you observe something happen, you can see where things started at before the thing you observed happened. For example, if you watch something fall, initial conditions would be, it started here and then it fell down there. We'll talk about why that's important later. But for right now, step 3 is just hypothesis. Have an idea about why something happened. And hypotheses can be garbage, if I'm being honest. Perhaps some human millennia ago figured that apples fall out of trees because they're scared of birds, and the apple's just trying to get away from the bird. It's not a great hypothesis, but it is still a hypothesis, so you're still employing the scientific method. And what you do with your hypothesis in step 4 is you experiment to see if your hypothesis is correct or not. And an experiment is arguably the most important part of the scientific method, because that's where the data comes in. To do a good experiment, you have to list out exactly what you're going to do, what things are like before you do the experiment, what you do during the experiment, what happens as a result, and you have to be recording data the entire time. To paraphrase Adam Savage, the difference between science and messing around is writing stuff down. You gotta record all of your data. If anything happens, you want numbers about what it was that happened, both before and after. And the experiment, the data collected within the experiment, is what you use to figure out if you had a good hypothesis or not. So, let's look back at our garbage hypothesis about why apples fall from a second ago. Say if we hypothesize apples fall out of trees because they're scared of birds. How could we test that? Say we watch an apple all day, we have an apple orchard, we see an apple hanging from a tree, and we observe what happens every time a bird flies overhead. When a bird flies overhead, does every apple in the orchard spontaneously yeet itself towards the ground? After observing the orchard for a day, we could probably conclude no. About 9 times out of 10, there might not be a correlation between bird overhead and apple falling down. And so the data at that point would be 10 birds flew overhead, only about once could I correlate that to an apple falling. So in that case, we look at the data, match that the bird being present didn't quite sync up to apples falling. The data there would be, again, how recording apples falling connected to bird presence. And in that case, the data didn't quite support our hypothesis. If the data doesn't support your hypothesis, you go back and you try to form a better hypothesis. You've got data now, you can use it to try to inform your next guess as to why apples fall. And then you do another experiment, you collect more data, and you keep refining, getting better and better ideas until eventually you land on one that sticks. You get a hypothesis, and the data actually supports it. What happens then is you do it again. You keep checking to make sure your hypothesis is good. You keep performing your experiments. You keep collecting more data. And eventually, when you find that hypothesis that just keeps working out, you tell people about it, which is also pretty easy these days thanks to technology, because you can just post your findings directly to your social media platform of choice. So, technically, posting stuff online is also good science. You share your findings with the world, and other scientists at that point will try to replicate your findings. They will test the same hypothesis, do the same experiment, maybe tweak one or two things to see if your hypothesis is still sound. And if over time, all of those scientists keep testing your hypothesis and keep finding it to be good, if their experiments keep matching your idea, that's when your hypothesis evolves Pokemon style into a theory. And then, if after a century or so, your theory keeps being true, people keep testing it, keep doing slight alterations to your experiment to keep finding out if it still works. After a century or so of repeated experimentation across scientists across the entire planet, if after that period of time everyone still thinks it's good, then your theory evolves into a law. And so this is the list of steps to do good science. This is the list of steps that gets the laws of physics recorded into textbooks. Questions so far? All right. Now, as it relates to this course, I will say again, the most important part of this method that we are going to be employing is the experimental and the data stage, because the data is the most useful part of this method. We need data, we need numbers to calculate with, to try to figure out what's going on and to make predictions about what's going to happen next. If we're doing a question about hitting a baseball with a baseball bat, we need data about the mass of the ball, the force applied to it, what direction that force is pointed in, to try to figure out what direction the ball is going to take off in and how fast. So the data is the most important part. The data is the part we're going to spend the most time thinking about this semester. But there's an important quirk of how these laws work that I want to spend today talking about. And I want to go through them in reverse real quick to try to make this observation. Laws of physics are the last step in this chain. Every law of physics sits right here. And if we go backwards, every law of physics was at some point a theory of physics. And if we go back even further, every theory of physics was a hypothesis of physics. And a hypothesis is just an idea, right? Hypothesis is just a fancy word for an idea that a human came up with to try to explain something that happened. That means that every single scientific law started out as a hypothesis, and every single hypothesis is just an idea generated by a human. Yes?
What are some examples of physics hypotheses that are new or still trying to be proven or experimented on that you know?
New hypotheses.
I feel like physics is kind of
Well, okay. Let me mention the one that popped into my head first. And when I say new, this is technically within the last century. physics is kind of slow. Relativity, the work made popular by Einstein, excuse me. Einstein's biggest, most famous contribution to physics was general relativity, the idea that space and time are relative to where you are in the universe and what happens to be close to you in the universe. Bless you. And I'd say an even newer hypothesis from that would be quantum mechanics. These things have been what are developed within the last century or so. And because they're so new, we are still working on exactly how we can make use of them, exactly how they work necessarily. Within the field of quantum mechanics, one of the biggest mysteries is how, is gravitons the mysterious one? Quantum particles is not my specialty. Within quantum mechanics, I believe gravitons are very poorly conceived, or poorly measured. A graviton is this theoretical particle that travels between objects with mass to carry the force of gravity, basically. Within quantum mechanics, there's always a particle responsible for everything. And the issue with the hypothesis of gravitons is we've never measured the presence of one. People believe they exist, but we've technically never measured one existing. So I think off the top of my head, that might be the most recent hypothesis that we're still having a hard time with. The quantum explanation of gravity keeps eluding us. Does that answer the question?
Yeah.
Okay. And I'm glad you asked that, because I actually kind of want to take what you said and go even further back. Every law of physics started as a hypothesis, and that means that every law of physics is really just an idea that a bunch of scientists think is true. Physics is the study of the universe, the scientific academic study of the entire universe, and the universe is big and mysterious, and it's going to do things whether we understand them or not. Right? Before we ever had any understanding of gravity, things would be falling. Newton didn't discover gravity, he just did math for gravity. People have been noticing things falling, since humans gained sensory awareness, right? Like, the idea that things fall was not the revelation. And Newton wasn't even the first person to do math about gravity, he's just the European that got famous for it. But every law of physics began as an idea, an idea about an observation. And because, technically, all laws of physics began at this hypothesis stage, every law of physics is flawed because humans made them up. That's not to say that humans have any control about how the universe works. The universe will do what it will do. The problem is that the laws of physics are how humans think the universe works. Gravity isn't a hard and fast rule, it's just our best guess as to why mass accelerates towards other mass. We have observed mass accelerating towards other mass, and the law of gravity is our best math, our best educated guess about why that happens. And because it started here at the hypothesis step, an idea conceived by a human, all of physics is inherently flawed because humans made it up. Humans invented every single part of science because science is just our current best guess about why things happen, our best attempt at explaining and studying the universe. It's not to say the universe isn't real. We didn't make up the universe. But our interpretation of the universe keeps changing with time as we keep getting better and better about our hypotheses, our observations, our data collecting. The laws of physics are not hard and fast. The laws in physics were written by humans to best understand the world around us. They're our current best guess, and they can be flawed. I want to tell you now about a case where physics was just wrong and we had to fix it. So, story time. mentioned Einstein a minute ago. Einstein gave us relativity, and before we had relativity, we go centuries back to Newton. Newton, pretty famous guy, got famous for writing about forces and gravity and a bunch of pretty important stuff that we still use today. We're going to be using a lot of his equations in this class. Newton, again, to kind of summarize, most of his work had to do with force and motion. And his work, which I would call Newtonian mechanics, became very foundational to how Western science perceived the entirety of force and motion, pretty much most forces and most forms of motion. And Newton's equations and the work that followed them were so good that for hundreds of years, they were the gold standard for how we would track motion both on planet Earth and in space. Newton's equations allowed us to figure out the trajectory of the planets in our solar system. Because, again, they're about force and motion. We were able to calculate the gravitational force from the sun on, say, Jupiter, and we could figure out where it would be the next night. And Newton's equations were great. They worked to track the motion of every single planet in the sky, even eventually allowing us to figure out that Pluto existed. We only discovered Pluto within the last century because, it's so far away and it's so dark, we just couldn't see it until we got better telescopes and could predict its motion. So Newton's equations were great. For hundreds of years, they were laws of physics that we used to map every single planet within the solar system within the night sky, except one. Can you guess which planet we could not accurately predict the motion of? Any guesses?
What, Earth?
It's not Earth. It's a good thought. That'd be the most shocking option, probably. We can't predict the motion of our own planet. That'd be an interesting narrative book. It's actually Mercury, the one closest to the sun. For some reason, Mercury was never where we expected it was going to be if we used Newton's math. It just never synced up. And for centuries, couldn't think of why. Until someone had a hypothesis. I'd say, 200-300 years ago, someone had an idea. Someone used Newton's math, did a bunch of very hypothetical calculations to figure out that if there was an extra planet in the solar system, its gravity would be affecting Mercury's orbit in such a way to create the results that we're seeing. Now, there's no evidence that such an extra planet actually exists. They needed Newton's math to work because they had no alternative at the time. There was no better law, there was no better hypothesis to explain the motion. They didn't want Newton's laws to be wrong because it's all they had at the time. So they kind of bent over backwards to figure out some way to make them work. So without any evidence of this extra planet existing, they did a bunch of very theoretical math to figure out that if there was this secret extra planet within our solar system that was always conveniently on the opposite side of the sun from planet Earth, so that we could never see it, its gravity would affect Mercury's orbit. Now, does it sound like a good idea to say that there's an extra mystery planet that we can't see because it's always on the other side of the sun from us? No, it's not good math, it's not good science. Because if it was this close to the sun, it would be orbiting at a different rate to us. So at some point, it would zip around faster than we go around, and we should be able to see it at some point. Like, the presence of this planet doesn't make any sense. But they were willing to overlook that fact because they needed Newton's laws to work because they had no alternative. They didn't want to admit Newton could be wrong because it's all we had. So they just assumed this planet must exist. Want to know what they named it? Keeping in mind that our solar system has kind of a Roman theme for most of its planets. Any Star Trek fans in the audience? Vulcan. For a minute, there was actually a planet Vulcan on several of our solar system's planetary charts because scientists just assumed it existed. Should have found this image before class started. Vulcan, hypothetical planet. Right there. Just between the Sun and Mercury. Now, Vulcan doesn't exist, unfortunately for Spock. But for a while, a lot of people wanted it to, because it was the only way that Newton's laws could predict the motion of Mercury. So, because they just assumed it had to exist, they put it here. They taught this. Before Pluto ever existed, there was already 9 planets, apparently. Now, eventually, we got better telescopes and better satellites, and when we looked around the other side of the sun, guess who wasn't there? No Vulcan, no planet Vulcan. Now, the creator of Star Trek does homage the idea of Vulcan, and that's why in Star Trek, Spock's homeworld is named that, so it is a reference. But Vulcan doesn't exist. There is no extra planet there. Newton's laws were wrong. Because Newton's laws started as just ideas in his head based on flawed information, flawed measurements. There were things that Newton could not have known about. And that's why Newton's rules didn't work here, because there's things that he couldn't have taken into account that might have affected something like this. And that's when Einstein came along and gave us general relativity. There were things that Einstein was able to figure out with new tools, better measurements, better data that allowed us to actually figure out what was going on here. That better data informed us to the fact that space and time bend. Space and time are relative to where you are in the universe, and that's why the idea is called relativity. Now, relativity is not on this semester's course list. Like, it's not something we're going to have to do math for, but just very briefly, if you've ever watched Interstellar, relativity is the idea that the closer you get to a big object like the sun, time slows down and space gets, well, you get timey-wimey and spacey-wacy. Those are weirdly technical terms for what's going on here. Not Vulcan, Vulcan's not real. Mercury is basically trapped in a time well. The sun's gravity is so strong, it has changed what 1 second means for Mercury in comparison to what it means for Earth. Time on Earth and Mercury do not pass at the same rate because the sun's gravity is slowing time down in this quadrant of the universe. There's no way Newton could have known that. He had no data for that because we didn't have tools to measure it at the time. But a couple centuries later, we had better data, we had better tools. The data was the thing we needed to trust. There was no data that Vulcan existed, but there is data about Mercury's time dilation. And so that is the flaw of the scientific method. No matter how good your laws are, they're just started as ideas. And the data is the closest thing to fact you can get. Yes?
Do we know how severe the time difference is?
Off the top of my head, I do not. But do you have the internet? Hold, please. Okay, it's about 2% slower there, if I'm reading this right, which isn't a lot, but it's enough for us to miscalculate its orbit over a long period of time. Not a lot, but enough. Enough to, bug scientists. To tie another piece of science fiction into this, it's not just gravity that bends time, it's also speed. So relativity is not just about gravity, it's also about how fast you're moving. And that's the hand-wavy explanation for why the Flash can time travel. The better fictional representation is weirdly the Lightyear movie. Buzz went too fast, he wound up in the future. But you can't go backwards like how Flash can. But you speed up to near light speed, time slows down for you in comparison to the rest of the universe. We have tested that, actually. We put a stopwatch in a satellite. We started 2 stopwatches at the same time, put one of them on a satellite, sent the satellite up, spun it around the Earth as fast as we can, going several times the speed of sound, brought it back down. Less seconds had passed on the satellite one than on the Earth one, because the faster you go, the weirder time gets. Again, we could not have data for that prior to the last couple of centuries. Newton couldn't have known about that, so there's no way that Newton's math could have accounted for it, and that's why Newton's laws were wrong in this specific case. In science, it is crucial to be able to admit when you don't know something, or else you get planet Vulcan. Yes, sorry.
How big of a difference was it whenever they did the stopwatch experiment?
I couldn't imagine it would be a very big one. It would probably be like a second or 2 on an atomic clock maybe, but any difference would be a big deal. But let me try to check real quick if I can find data from that experiment. Okay, if the data for that is publicly available, I cannot quickly find it, unfortunately, so sorry about that. But this is why it's also a good idea to do your own research, because an important part is the research. I'll see if I can find that data though. But main thing I want to focus on for right now is the data is the most important thing, and that's why we're going to be focusing on math for this particular class, using the data to try to make assumptions and predictions. And the laws themselves are flawed. They are malleable. They change with time as we get better data, as we have better understandings of the universe around us. So this anecdote is meant to teach you that it's okay to be wrong. It is okay to make mistakes in this class. The problem is when you don't admit you've made a mistake and don't fix it. Because if you don't do those things, you end up with planet Vulcan. And then you teach centuries of kids that there's a planet that doesn't exist. So, in your own math for this class, whether it's in your notes, on your homework, or on tests, it is okay to make mistakes. It's a part of the process. You only get better, you only improve at the math, you only make better assumptions as you make mistakes and eliminate what doesn't work. So, you're allowed to mess up in here. I will help you fix it. It's part of the process. Cool? Questions? All right. A couple more things about scientific method before we wrap up for today. Physics is an operational science, and that word just means that to do a very good experiment, you need to know the initial conditions before your experiment begins. You have to record the state everything is in before you press go, record data about what happens as a process goes on, and then make sure you also conclude data about where things end up at the end of your experiment. To do good science, we need data, and you need as much data as possible throughout the entire process, because the data is as close to fact as we are able to get. So we need to make good measurements, a lot of good measurements. We're going to talk about measuring and unit conversion in math on Friday. And you're going to need to record a lot of it, and we're going to have to use it in our math. Now, words, excuse me. Science gets a little fuzzy. One, when you won't admit that you're wrong, because again, that leads you to planets that don't exist. But 2, it gets a little bit fuzzy when you don't know your initial conditions. What I mean by that is, we talked earlier about, early observations of gravity. People can see things falling. If you observe this golf ball to be here and then watch it fall, you know that its initial condition was right here. You have data, or at the very least eyewitness testimony, that it was here and that you watch it descend. But let's say instead of any of you seeing the golf ball at this point and then falling, let's say that you enter the room and the golf ball's just here. Do you have data for the fact that it fell into this hole in my desk? Without knowing its initial condition, it's really hard to actually guarantee with any real certainty how it got there. You can see that it's there, but you don't know when it got there or how it happened. It could have always been there. I could have perfectly 360 threw it exactly into this spot from the hallway. You don't know. You don't have that data. If you don't have initial conditions, you can't do good scientific method operational science. If you don't have initial conditions, that's called a historical science, because the purpose of historical science is to look at the present data and try to figure out your best possible guess about how that thing got there. Now you look at this and it's a reasonable guess that maybe it fell there, maybe I just placed it there. Someone could guess that it's just always been there since the dawn of the planet, which it's not a good guess, but it's a guess. Without the initial conditions, you can't say for certain. So in this class, we want to do operational science, we want initial conditions, we want as much data as possible to inform our conclusions. If you don't have initial conditions, you are performing historical science, which includes things such as archaeology, because we know that there are bones in the earth, but we don't know exactly what that creature was doing before it got fossilized, or everything about it. All we have left are its bones, or rather, the rock castings of its bones. Meteorology is also a historical science, because you don't have the initial conditions of every single gas particle in the atmosphere. And that's why the weather report is frequently not totally accurate. Not only do you don't know the initial conditions, it's kind of hard to predict the chaos of wind, among other things. So, we like data in this class. Data is as close to fact as we're going to get. We want as much data as possible, including initial data. So on Friday, we're going to look at taking data and how we're going to be working with numbers in this particular course. Any questions at this particular time? All right. As I said, next time we start on data and numbers, we're going to go over, this is just a sneak peek, we're going to go over units and the metric system. We haven't dealt with science much. We like metric because, well, it's not very American, but it is a bit more scientific. So we're going to review the metric system and all that good stuff. Let me know if you guys need anything between now and Friday. Friday's when our math and numbers will properly start. Have a great day. Stay warm. Stay safe. Thanks. Yeah, whenever you miss one, just try to check out the notes and watch the recordings.
Have a good day.
Thanks.
I'm sorry.